For those who don't know me, let me start from the basics. Quantum many-body field theory. Okay, my name is Jonathan. Rookhman, and this is my email. There is a web page with the same name. If you just search this name online, then there's a web page, and on the web page there's also a link to a page devoted to this course. Before we start, okay, maybe I'll start with the topics, and then I want to ask you something about the timing of the course. Let me see. Okay, so the first thing I want to say, a disclaimer: I don't consider myself an expert in quantum field theory. I'm barely someone who uses it. Okay, now this is a problem here in this specific university. We don't have high energy physics, and someone needs to teach it. So the way I'm going to do it is every week I'm going to choose a different topic, try to cover it. Maybe each topic will take 2 weeks. Sorry, maybe some of the topics might take longer than 1 week. And I really want to view it as an open discussion. Okay, I'm not, maybe some topics I know better, maybe some topics I know less, but I want to view it as if we're all learning together. I gave a course 2 years ago. I think it wasn't very good. It was, I was very busy when I gave it. I'm very busy now. So I hope, but I really hope to improve it this time. So the topics I chose are, the first topic we're going to cover today is the Klein-Gordon field theory. Today. Then the next topic is going to be the Dirac theory. The main reason I'm doing the Dirac theory is because I understood that in the advanced quantum mechanics course we took with Taurat, Dirac wasn't covered. Right. Okay. So you need to study it at some point. So I'll do that. Then we're going to do many-body path integral approach to compute the partition function. So this is using quantum field theory to compute partition functions for quantum theories in thermal equilibrium. Okay. Then we're going to do perturbation theory. And this includes, Feynman diagrams, symmetry breaking, although symmetry breaking is not exactly perturbation theory, but it will connect nicely. Disordered field theories. Okay, then topic 5 is going to be a renormalization group. Okay, renormalization group is a classic example of something that, for example, I'm going to teach you, thumb rules the way I understand it, but it's much more, when it's done properly with gauge invariance and all that, it's done much more rigorously, and I don't know how to do that. Maybe we'll try to even take care of that. Maybe we'll learn together. And then topology in quantum field theory. And if there's anything you want to cover that interests you, this will probably cover the entire course, but maybe if we have time, or if you feel there's something more interesting you want to look into, this might change. Okay, so these are the topics I want to cover. Now, I just wanted to ask, is there any chance that you have a problem with changing the time of this lecture? Because for me, it's a bit too early in the morning. Is it a problem for anyone here, at least, to push it to the afternoon today, for example? Is that a problem?
So
we can do it at post 4 p.m. I don't know, like 3 p.m. 3 p.m. to 6 p.m. Is that okay? Okay. Okay, so that I need to still, it's not final because I need to verify with the other 3 students that are registered for the course. Okay. Yeah, and okay, so books. So these 2 topics, I'm going to use Peskin, and this is this book. Schroeder. This here, these 2 topics, I'm going to use Altland and Simons. And these, I might also use other book like Doniak. We'll see. And here also, I think I'm going to use Altland and Simons. And in these books, there are exercises. Because I don't have time to write an exercise every week and so on. So what we're going to do is after class, either I send you an email or at the end of the class, I'll tell you which exercises at the end of the chapter to solve. And you can hand that in. I'm not going to be super strict, but I think like a 2-week period is reasonable. Okay, sounds good. Okay, so now, unless you have any other questions, we can start. Yes.
Will the recordings of the lectures be uploaded to YouTube?
Okay, naturally, yes. I wouldn't expect otherwise. So I think yes, but in any case, on my webpage, I'll have links to all these things. All you really need to know is my name. Anything else? And I don't know if every lecture will be exactly the whole 3 periods. For example, today we might cover in a shorter time. But that's what I prepared for today. Okay. Can I erase this? Okay, so what we want to do is the Klein-Gordon theory, which is a good introduction to quantum field theory. Now, what's the point? The point is that I don't need to explain the advantages of field theory. Okay. So for example, classical, let's say classical field theory there are a lot of advantages, right? We have the hydrodynamics, electrodynamics, wave phenomena, what else? I don't know, like elasticity.
Optics.
What?
Classical optics.
Classical optics. Yeah, well, that goes in electrodynamics, classical optics. Elasticity. Anything else? There are much more, right?
Gravity.
Gravity. Wow, that's a exotic one. Liquid crystals. Anything else? I don't know. Have any ideas? There are probably much more. But the point is that just from classical theory, we enjoy the ability, the power to describe many different phenomena using fields. Fields are very important. Okay? We can't describe everything in the terms of particles. And the quantum field theory is basically about, using the same notions, using the same thing in quantum theory. Basically quantizing. So if you remember when you started quantum mechanics, I don't know how quantum mechanics was taught to each and every one of you, but you start from classical mechanics. You take these position and momentum, or position and velocity, which are the basic, right? You start basically from Lagrangian and Hamiltonian classical mechanics. There you have P and Q, which are the location, the position, and the momentum, and you quantize them. And the idea is the same thing. We want to do the same thing for this Klein-Gordon theory. Okay, so this gives us a reason, like motivation to use quantum field theory is just to have the same power to describe phenomena like this, but quantum. Okay, so imagine that, I don't know, quantum elasticity, okay? A quantum phenomena in waves, we would really want to have quantum gravity, for example. Okay, so this is a general challenge, and it's always very exciting and interesting. And when it becomes quantum, it shows new phenomena. So it really is typical that that when we go quantum, we have more. Okay, we get things that are unique, and there are two. I think there are two things. One of them is that it's, as physicists, we're always striving to understand new phenomena, but also an interesting thing is that unlike classical physics, for quantum physics we don't have good intuition. We need to develop it with time, and that's also something that is very important. But in any case, all this is kind of very powerful motivation, but a bit vague. So following Peskin, there is a very concrete motivation that we can give, and that is a challenge that was faced early on, is writing a relativistic quantum theory. So it turns out that just trying to write, trying to have a relativistic quantum theory, we had Schrodinger's equation. It's not relativistic, right? I'll show you in a moment, but it's obvious that it's not relativistic. Just wanting to have a relativistic theory already pushed a scientist, physicist, to develop quantum field theory. So that gives us another motivation. And, so why is this so? So one thing we can look at. So by the way, when I said that you didn't learn Dirac, I was under the impression that you did learn path integrals. Mm-hmm. So you know what the propagator is. Yes. So if I write the propagator, k of x and t, x prime and t prime, okay, this is basically the quantity that minus IH t minus t prime x x. So what this quantity represents is initiating a particle at x. So it's certainly located at time t at location x, then evolving it up to time t prime, okay, and then asking what is the probability of observing it at x prime. And this is not a probability, this is a probability amplitude. So it can be complex. And this can be computed very easily because this propagator is, you know the answer? Does anyone remember? Do you remember it? Let me ask you a different question. If I ask you what the propagator of the diffusion equation is, do you know? Tell me.
You need to expand in the eigenvalues of the energy.
You need to expand in the eigenvalues. No, I'm not. Well, I'm asking more. I'm asking more than that. I'm asking not how to compute this. So this can be computed in many different ways. Okay. I'll show you a quick way now. But I was just wondering if anyone remembers by heart.
You need to sum of the whole trajectories.
It is okay. We can cast this into a path integral. When it's a path integral, it's a sum over all trajectories, with each one weighted with its action. Mm-hmm. Yeah, that's okay. That's something I'll put in your exercise to remind you some path. But there's a quicker way is to identify that this is basically a propagator of the Schrodinger equation. Okay, so if I write the Schrodinger equation, it's dt, right, minus, sorry, by the way, I forgot to mention, it's not fair to even ask you this question because I forgot to mention that, I'm looking for this propagator for a free particle. Okay. For a general particle, of course, you don't. Okay, sorry. So now that I said that it's a free particle, now anyone knows the answer?
Right. It's just to put the one it minus, well, it's 1.
You mean that I just put here p squared over 2m?
Right.
Right. But do you know the answer in terms of t minus t prime and x minus x prime?
You need to open it to Taylor series where p squared and x are not commuting, but they have the relation of IH bar, and that gives you.
Oh, you don't have to do that. You don't have to do it.
You don't
So there are many different methods.
You can use Baker-Cameron.
You can use. Okay, so if you use path integral, if I would do a path integral, then I would basically write e to the minus I p squared over 2m t minus t prime. I would write this as e to the minus I p squared over 2m times delta to the power of n, where n is equal to is equal to t minus t prime divided by delta. Okay, then when I take n to infinity, this delta becomes tiny, and then I can basically open up this into a product of these guys and stick in resolutions of identity and do all this trick which gives you a path integral. But what I wanted to say is that there is a quick and dirty way to compute this, which is to identify, using prior knowledge, of course, using the fact that this is h bar over 2m Laplacian, right, acting on psi of x and t is equal to 0, and you can identify that this is related to the diffusion equation, right? Rho of x and t, okay, and we know that the propagator is basically the Green's function. They're the same thing, and the Green's function is the solution to a delta function. And I don't know if you remember this, but the propagator of this guy, let's denote him by d of x and tau, is equal to 1 over square root of 4 pi dt e to the minus, and this is to the power of d, whatever your dimension is, minus, let's say, x squared over 4d tau. This is tau, I said tau. I'm sure that you saw this expression before, right? So now all you really need to do to compute this thing is to identify that, okay, so there are two ways to do that. So we can identify that d is equal to h bar over 2m. That's the first thing, right? And the second, divided by I. We can do that also. We can do that. Okay, maybe we can do that. Divided by I. Okay, so what we want to say, okay, let's do this properly. So let's call this d tau. So if we do d tau Laplacian acting on this d of x and tau, the claim is that we get delta of x minus x tag 3. Okay, so let's put this 3 delta of t minus t tag. Okay, so now all we really need to do is make a change of variables. So we can do analytic continuation on tau, and we need to multiply everything by h bar, right? So we can write, say h bar, and then we get an h bar here. And then d takes this this value. Okay, and tau is equal to, here the sign is always confusing, and tau is it. Okay, so then it means that in this expression, all I really need to do is write d of x and it, and substitute this d. So I get 1 over square root of 4 pi. So let me write it like this. M divided by 2, right? 2 h bar. it to the power of d over 2 exponent of minus x squared. Again, we have here, so we have 2m, so it's m x squared divided by 2 h bar, and this whole thing comes with an I, so it's I t, like that. Okay, and that's indeed your propagator. So here this x, maybe I'll write it like this, d of x minus x prime and it minus t prime. Okay, so then this is t minus t prime, and this is x minus x prime squared, and this is t minus t prime. And you can open your notebooks from advanced quantum mechanics, and you'll find that this is exactly the expression. Okay, so this is basically using analytic continuation, right? The solution of this equation and of this equation are the same. But in the exercise, I'll give you to also solve this using the path integral to remind yourself. But one of the things that we see in this expression is that if I look at the probability amplitude, okay, there is a probability for a particle to be anywhere in space. Okay, that means that except exactly at t equal to 0 where it's a delta function, okay, afterwards it can be infinitely far away. There's a finite, exponentially small, but finite probability to find the particle infinitely far away. So this is obviously not relativistic. Okay, and now we want to write it in a relativistic form, and one of the first things that people thought was, maybe I'll, where's the eraser? Okay. Maybe I'll remind you how this result is obtained. So the way you obtain this propagator is you write the Fourier transform d3k over 2 pi squared of e to the I k x minus x tag e to the let's say minus I h bar squared k over 2m. Sorry, this is I erase 1 h bar, and then we have t minus t prime. Okay, so this integral gives you, if you calculate this integral, you're going to get exactly this d of x minus x tag I t minus t. Okay, and one of the things that people thought that could help is that if instead of this we can view this thing as a dispersion relation. E of k is equal to h bar k squared over 2m. People thought, okay, maybe if you write a dispersion that is relativistic, okay, E of k, which is equal to, say, square root of c k squared plus c squared m squared, something like this, then you would obtain a better result, a result that decays. And it does help. It does help in the sense that what you will find then, that there is a light body. Okay, you'll find that if you look at space and time, this is say t and this is x, okay, you'll find that there is a light cone, ct, or x over c, where here you have oscillations or some finite probability, and here you have exponential decay. So at least you have a light cone in this propagator if you compute it. Maybe we'll also give this as an exercise, but you still have a finite probability of finding particles outside the light cone, which seems to violate the most basic notion of relativistic theory. Okay, so this is, if you like, the problem, and now this motivates us. This is basically the motivation I was talking about to develop a quantum field theory, and what we'll see both at the end of this class, or at least I'll give you a path how this is solved in quantum field theory, and in the exercise you will make it happen. Okay, so this was also just motivation. Any questions?
Can you use, instead of thinking about the momentum on the four momentum?
You can. We'll see that. But in what sense? You're asking if instead of doing a Fourier transform in 3 dimensions, I'll do it in a 4-dimensional space?
Right, and instead, here we assume that we're living in the 3D momentum, right?
Yeah.
We can just translate it into
the answer is that won't solve the problem. We will write expressions like that. In the end, what really solves the problem is, we'll get to that in the end of the class, but you need to ask yourself, what do you mean by causality? And for that, we will need to introduce fields. What we will do is we will introduce fields, and we will see that what really vanishes outside the light cone is the commutation relation between fields. And if the commutation relation, if they commute, if they're outside the light cone, it means that they can't affect each other. They're not connected. Okay. That's basically the answer. Thank you for the spoiler. No, but we'll get to that. Okay. Okay, good. So let's start. So what we're going to start with is the essentials of classical field theory. So I'm going to do a short reminder. Essentials of classical field theory. So the first thing I'm going to remind you is Lagrangian formalism. Okay. So in Lagrangian formalism, we have this object which is called the action. Okay, the action is a scalar, basically, it's an integral over this object called the Lagrangian. And typically, if we're describing a field theory, then the Lagrangian is a special integral over what we call the Lagrangian density. We have an integral from 0 to t tag d dx over all space over the Lagrangian. So this would be t tag and x, Lagrangian density. And then the idea is that the classical equations of motion, basically this action and this Lagrangian are constructed in a way that the saddle point of this action, minimum action, in this case it's not even a saddle point, it's just the minimum. The minimum of this action is gives us the equations of motion. So if you remember, the idea is to write delta S. Okay, so I'm reminding you I'm varying S by, oh yeah, this is also important before I write that. So I want to assume that this L, okay, it is a function of some field. So we have phi, and then we have d mu phi, okay? And d mu, right, d mu is basically like dt, and so I'm going to use this notation. Did you ever see this notation?
Yes.
So now I want to vary S with respect to these fields. Basically, I'm going to change phi a little bit. Okay? And if I change phi a little bit, I'm going to get that this guy is d4x. d4x now denotes both integral over time and space. And then I have, so the obvious one is dl to d phi plus dl to d mu phi. Okay. Oh, sorry. Delta phi plus dl to d mu phi delta of d mu phi. Okay, so it's kind of like I changed both, but now I'm going to do integration by parts on this one. It's funny that I don't know, a couple of weeks ago I had to compute a saddle point of some functional, and it took me a while to remind myself that actually this is how you take the saddle point. You have both derivatives and field, but now we do integration by parts, and we get three terms. We get an integral d4x, probably dl, you guys can help me, minus, now I'm doing the integration by parts. So I get d mu dl to d mu phi. Okay, this whole thing is proportional to delta phi. This is the bulk term. Okay, and in addition to that, we have some boundary term, d3x boundary. I'm not even specifying exactly what that is, which would, yeah, which would be the boundary. So the boundary term is where we multiply both of them. I'll talk about these boundary terms later. So it's something like dl d mu phi times delta phi on the boundary. Okay, so it depends. If you have a boundary, then it's going to be some perpendicular. So this thing is actually like a vector. Okay, maybe I should write d3 mu like that. Okay, and this is like a vector product between the two because it's like a boundary term. But we'll talk about these boundary terms in a second. Now, assuming there are no boundary terms, then we see that the vanishing delta s, delta phi equals to 0, gives us that delta L to delta phi is equal to d mu d mu phi. And these are the equations of motion. Okay. Good. So that's the first thing. Now, maybe we should do an example. Let's do a quick example, and then so let's take L is equal to rho over 2 phi dot squared minus C plus n squared minus omega naught phi. And this is the Klein-Gordon field theory. But just as a comment, so this guy here is like mass density of the field. This is the velocity, right? And this is the mass. Now, not to confuse with mass density. You can think about this as like frequency. What do I mean? So this field theory, for example, shows up. I just had a dispute with some scientists about something, and I wrote a comment on arXiv. And this is exactly the theory I used to describe optical phonons close to the zone center. So if you're looking at a crystal, then of course if you go to very short wavelengths, meaning you go close to the edge of the Brillouin zone, then there's a lot of issues that have to do with the symmetry of the crystal. But if it's a cubic crystal, for example, it turns out that close to the zone center, this is all you have. So you can write a theory for very long wavelength optical phonons. This is the theory. So it's not only some relativistic field theory, high energy, blah, blah, blah. It has even applications in condensed matter. And it's a very, what I'm trying to say is that it's a very generic theory. Okay, it appears a lot.
Shouldn't it be phi squared near the omega?
Phi squared, yes.
Oh, okay.
Yeah, if it would be phi, that would be problematic. Okay. Yeah. So let's obtain the equations. So first of all, we can write phi dot squared minus C phi squared as d mu phi d mu phi. Okay, assuming that this g mu nu is something like 1 minus C minus C minus C, something like that. Okay, and yeah, please stop me if there are any mistakes. And then dl d phi is just minus rho omega naught squared phi. But this thing should be equal to d mu dl to d mu phi, which in our case is just d mu phi. Okay. So our equation of motion is basically dt squared minus c squared this whole thing times phi equals equals a rho omega naught squared times phi. This is our equation. Or I can just put this here, plus omega naught squared. Yeah, I forgot. There's a rho here on everything, and then this thing multiplies phi equals to 0. This is rho. Forgot the rho here. Okay. Okay, now next thing is I want to discuss no ether theorem. You all encountered this as well? Okay. Where, by the way?
In the first course.
Nice. Okay. So the idea behind this Noether theorem is that we have a symmetry. Okay, so if the Hamiltonian has a continuous symmetry, then the statement is that there is going to be an associated conserved current, forecurrent, which means that there's a conserved charge and a conserved vector current in 3 dimensions. Okay, and now we're going to show that. So, for example, for this theory that we wrote here, you can notice sorry. Yeah, so if the Lagrangian has a continuous symmetry, okay, and I'll explain in a moment what that means, then there is an associated conserved forecurrent. So what I mean is that there is a current J mu such that d mu J mu is equal to 0. So first of all, what do we mean by a symmetry? Imagine that we perform some change. Okay, so phi of, say, x, or phi of x, that's right, phi of x, mu, goes to some phi prime of x, which is equal to phi of x plus some alpha delta phi of x. Okay, so this is a small variation of the field. Then we expect that under this transformation, delta of x. But okay, this is an example. Why do I say that it's an example? Because it doesn't have to be a variation of the field. It can also be a variation of the coordinate. Maybe I'll write it. So you can also have x going to some x prime, which is equal to the original x minus alpha, minus some alpha. Okay. And the point is that this alpha here is going to be small. So I want to assume that it's a small variation. Okay? Under these assumptions, under this transformation, we expect delta of x to go to some delta prime of x, which is the original, not delta, what am I talking about? The Lagrangian density will go to some Lagrangian density plus some alpha delta L. And how do I know that this is a symmetry? This is a symmetry if delta L is a boundary term. Okay? So it means that I can associate this delta L if the transformation is a symmetry, then delta L is equal to it's also some derivative of some current. Okay? This is not the conserved current. This is a different current. But the point is that if it has this form, when I integrate it over all space, it's going to be a boundary term.
Right.
Okay?
You use Gauss theorem, right? That's what you're using to convert it to a boundary term. Like you have you are integrating over all space.
Yes.
Then you have the derivative, so you can exchange it.
Yeah, exactly. Like before, it'll be a boundary term. Right. Sorry. No. Actually, okay. Now, why do we say that this is a symmetry? This is a symmetry because then the equations of motion. Remember that also in the equations of motion, we did not care about this boundary term. So if this is the case, it implies that the equations of motion are not changed under this transformation. And therefore, the physics will be the same. And therefore, we call it symmetry. Now, if this is true, then we can also make a vary directly. So for example, let's imagine actually what I said here is not exactly accurate. Actually, the two important things are this and this, and in fact this can be if I do a coordinate transformation, I can actually infer what is delta phi due to the coordinate transformation. Okay, so that was now I recall that actually basically if you want to find the Noether current, you need to know this delta L and this delta phi. This is the challenge. Okay, what we're going to need to figure out is what is this and what is this. And I know if you haven't seen this before, or if you don't remember, I know it sounds very vague right now, but we'll make it concrete in a moment. But the point is that what I can do is I can also derive this delta L by using this variation, exactly like we did before, right? Because what we're going to have is that alpha times delta L, okay? Just from that variation, we know already that it's going to be alpha times dl to d phi minus d mu dl to d mu phi, okay, times delta phi plus the boundary term. So the boundary term is just d mu times dl to d mu phi times delta phi, including everything. Okay, so this is the boundary term, and this is the equations of motion. And the point is, this was discovery by Noether, is that this vanishes, and therefore we can identify this term with this term. Okay, so basically what we say is that J mu is going to be equal to dl to d mu phi, right, delta phi So imagine that we equate this. Okay, maybe I'll do this a little bit slower. By the way, what I'm doing right now is something you know, or am I wasting too much time on this? Is this not familiar? So, okay, so let's say I equate this to that. Okay, so I write, let me remind myself. So I write alpha d mu dl to d mu phi, okay, times, times delta phi, okay? This thing has to be equal to this alpha delta L. That's basically what I'm saying. I'm saying that here we varied it specifically from how the fields transform, and here we did it directly from the Lagrangian. And therefore, if what I'm doing right now makes sense, then these two should be the same. Okay? Now, this, of course, cancels out. And you see that I can move this to the other side, use this notation, and therefore I get that d mu dl to d mu phi times delta phi minus this j mu, okay? This whole thing is equal to 0. So everything that's in this bracket is what I'm going to call j mu, and this is the conserved verb. Okay, and now let's see a few examples. Maybe it's a good time to take a break before the examples. I don't know. Let's do a few examples. So the first one is assume m is equal to 0. Okay, so I'm looking at this theory. Not m. Let's sorry. I will probably interchange between omega naught squared and m squared a bit. Okay, so sorry, no. Let's assume phi is a complex theory, field. Or, in other words, it could be, imagine that you would have this theory just with phi 1 and phi 2. Okay? Then you would have something like a continuous rotation between them if they're symmetric, but you can also write them as a complex field, like phi 1 plus I phi 2. And then this theory becomes, L becomes rho times basically d mu phi squared minus say this omega naught squared phi squared. Okay. Then in this case, we see that there is a continuous symmetry that we can this. Now what we want to infer is basically what is this delta L and what is this delta phi. And what is the symmetry? So the symmetry we see is phi goes to phi tag, which is equal to e to the I alpha phi, right? And this obviously doesn't change this theory. Trivial. And
alpha is a constant?
Alpha is a constant. Okay? Yeah. If I would want to make it not constant, I'd have to gauge the theory. Okay? And therefore, now remember that I didn't mention this before, but this term, we have multiple fields, then it has to repeat itself for all these fields. So for example, now we have phi 1 and phi 2, or phi and phi star, then we have to repeat it for phi and phi star. So we need two delta phis that we need to find. So delta phi is basically, we can infer it by expanding here. Right? We can write phi plus I alpha phi. Okay? And therefore delta phi is I alpha phi, and delta phi star is minus I alpha phi star. Okay? And the delta L in this case is what? Yes, 0. So this is a very simple case where delta L is 0. In the next example, we'll see an example where it's not. But this makes things much easier because then J mu doesn't have a contribution from this capital J. It's only this guy. Okay? So then we have that the J mu, right, is dl to d mu phi times delta phi plus dl to d mu phi star delta phi star. Okay, so now let's take these terms one by one. Oh, sorry, by the way, this is not delta phi. I made a mistake. This is delta phi. Right, because alpha is not part of the delta phi. Okay, alpha is the small variation. Good. Okay, so now this guy gives us this guy gives us, so we can infer, because we're taking a derivative with respect to d mu phi, it's gonna be like this: d mu, okay, phi star, and then multiplied by delta phi, which is I phi, and then this guy is gonna be plus, again, d mu phi, okay, but now I multiply by this. This is minus I phi star, okay? Or in other words, what I wrote here is just it's I times phi d mu phi star minus phi star d mu phi, which is nothing but the probability current, right? So if we write this yeah, you can also identify this with continuity. So you can, I don't want to erase this, but you can identify this with the continuity equation, right? Because the zero term, it's going to be like d0 d0 you could write this as d0, let me see, yes, so without a doubt, when mu is equal to j, 1, 2, 3, this gives us the probability current from quantum mechanics. But I think that it should be so, if I remember correctly. I didn't check this when I prepared this class, that if you write, I don't know, say n is something like phi squared, it's like the probability of this field, then this n, because what this transformation really tells us is that there is a conservation of probability, conservation of particle number, then we should get a continuity equation. Minus grad j, where this j is something like Vn. So that should, and this current is basically, okay, maybe I shouldn't write this. This is like a probability current, and this is density, right? So, and that's related to this symmetry. Okay, and then we can associate. I don't know if I had anything else to say about that. Let me see. Okay. No, I didn't have anything. Any questions before we do the second example? We will encounter this when we do, for example, symmetry break. Okay, we're going to use this result because there is a famous symmetry breaking. For example, the Higgs mechanism is associated with condensation. Let's say superfluidity and condensation is associated with breaking, spontaneous breaking of the symmetry. Okay, now let's do a second example. The second example is we also have another symmetry. Of, for example, Klein-Gordon is translation. So we want to write something like x mu goes to x mu prime, which is equal to x mu minus alpha mu. So alpha mu is like a tiny vector. Let me draw this for a moment. So what we imagine is we have some y and x, and then we have some alpha. This is alpha, and here we have a new x prime and y prime. So if I had, at a certain location, say this is x0 and this is y0, and here I have phi of x0 and y0, you see that in the new coordinates, this would be x0 plus alpha 0, and this is y0 plus alpha 0. What am I talking about? Not alpha 0. This is alpha 1 and this is alpha 2. Okay, so that implies that phi of x mu prime is equal to phi of x prime of x mu plus alpha mu, which is approximately phi of x mu. Okay, so this plus here comes exactly because of this drawing that I made here, plus alpha mu d mu phi. Okay. And then this guy is basically our alpha delta phi. Now, here is a perfect example where you see that this j doesn't vanish, because now when we do this coordinate transformation, we see that L is going to change. So delta L is not 0 in this case. Okay, so how do we see that? Yeah. So one thing we can do is we can really work it out. But on the other hand, we can say that L is a scalar. Okay. Sorry. L is scalar. And therefore, we know that the only way that L can transform under this is the same way phi transforms. So L, remember that this L is also a it's a function of x. Okay, so we have the same story. So basically, L goes to this x mu plus alpha mu in the same way, and therefore we get that it's equal to L of x mu plus alpha mu d mu L. So this guy is alpha delta L. And now we're ready to equate the two sides. Okay, so we say that d mu of dl to d mu phi times this delta phi minus, and you see very nicely now that this thing is our current. This is this J. And sorry.
This is kind of a Taylor series, right? In alpha.
Yeah, both of them are Taylor series. Yes. Alpha is small. This thing is equal to d mu. We have dl to d mu phi times, what do we have here? We have something like alpha mu d mu phi. Now I plug this delta guy in, alpha, and I have minus d nu, again alpha nu d nu L. Okay, so now to make, okay, this was from before, okay, now to make a connection to this equation, with this equation, I want to take out this alpha. So I have something like alpha nu d mu, and then inside I have dl to d mu phi, d mu phi, minus, now I need to write something like delta of, oh my god, sorry, no, this was like this. Okay, sorry, I want to take out this, sorry, I made a mistake. This is just this, okay? And now I want to take out this derivative and the alpha. I take them both out, but you see that here the derivative is with respect to nu, not mu. So I need to do something like mu, and then L. Okay, and this whole guy is equal to 0. So this guy is a tensor, right? It's T mu nu. And you know what this is?
Energy momentum tensor.
Yes. So it's not surprising that this is the energy momentum tensor because we made a translation in space and time. So the 0, 0 component of this would be the Hamiltonian, the energy density. The 0J terms are going to be the total momentum of the system. And the IJ terms are the stress, strain, whatever no one ever remembers. Okay? Now I can erase this. So this gives you a good, I think, understanding of how to use the Noether theorem. You basically need to very carefully verify what is delta L and what is delta phi. That's the job. Okay? So this is a T mu nu. T mu nu is equal to delta L to D mu phi minus delta mu nu L. And now let's look at an example for the Klein-Gordon theory. So T0, 0, for example, would be dl to d dt phi times dt phi minus delta 0, 0, which is just 1, minus L. And then the claim would be that this term is this, if I associate this guy with, you'll see in a moment, if I associated this with a generalized momentum or conjugate momentum, then this would be a term like pi phi dot minus L. So this is the energy, this is the Hamiltonian density, and we'll see this in a moment. Okay? And similarly, we can write T0J, for example, would be something like dl to d dt phi, okay, which again would be our generalized pi times the gradient of phi minus yeah, just that. It's basically just that. Okay, and if we look at that, that gives us pi times grad phi. This is going to be our total moment. Maybe there's a minus sign, I don't know. Don't catch me with a minus sign. Okay, so now the last thing I want to remind you before we quantize is to do the Hamiltonian formalism of classical field theory. Questions about that? By the way, I was talking to Asaf, and he told me that you guys actually never saw the quantization of the electromagnetic field. Is that true?
No, we saw it in advanced quantum mechanics.
You saw it in the advanced quantum mechanics. So you know what a photon is, and you saw it. So all this is just kind of. So the last thing is Hamiltonian classical field theory. So in order to transform from the Lagrangian field theory we just described to Hamiltonian, we need to perform a Legendre transform, but now we're doing it for a field instead of a particle. So we define this as dl to d dt phi, exactly what I wrote just there. Okay, and write h as integral d3x pi of x dt phi minus n. Okay, so let's do an example. So if we take our field theory from before, so I'll remind you, L is equal to rho over 2 phi dot squared minus C squared phi squared minus omega squared phi squared. Okay. Then pi is equal to dl to d phi dot, which in our case is rho phi dot, and therefore phi dot will be associated with pi over rho. So we just plug that in, and we get that H, the Hamiltonian density, is pi times phi dot minus, or maybe I can just write this as pi squared over rho. This is this first term, and then minus this guy again is rho pi squared, over 2 rho plus C squared grad phi squared plus omega naught squared phi squared. Okay, and then this cancels with that and gives me a square. So overall, what I get is just the energy density that we expect, which is plus rho C squared, rho over 2, rho over 2 C squared phi squared plus rho omega naught squared over 2 phi squared. And this is the Hamiltonian, which is associated with this Lagrangian, which is just the energy density. Okay, so that's the Hamiltonian. Now, everything we did up to now was just a reminder of classical field theory. Okay? And all the theories we took were very simple and quadratic. Now what we're going to do is we're going to quantize this Hamiltonian. Okay? So in quantum mechanics, right, we had x, say xl, and pj was I delta lj, and xl, xj was equal to pl, pj. Say we have a bunch of particles, then this is how we quantize it. We basically take the original Hamiltonian and introduce these operators that obey this algebra. So now we in analogy for fields, we're going to say that phi of x and pi of y is going to be I delta of x minus y, and this is a three-dimensional delta. And similarly, phi of x and phi of y commute, and also pi of x and pi of y commute. So now we have these operators, and the Hamiltonian also becomes an operator. Okay, so the Hamiltonian that we have here is just an operator. Okay? That's it, we quantized it. Okay, but now let's see what that means. So we can diagonalize the Hamiltonian. So we write H is equal to d3p over 2 pi cubed. So I'm using the first step is to Fourier transform this guy, and when I Fourier transform, this is say a continuous symmetry. It's not on a lattice or anything fancy like that. Then I get pi q squared over 2 rho plus plus rho c squared. Okay, maybe I'll write it like this. I'll write omega rho over 2. Let's write it like this. Rho omega q squared over 2 phi q squared. Okay, where this omega q is the square root of cq squared plus omega naught squared. And then we have some, this is q, this is omega q. We have like omega naught as a mass, that's why I call it an optical phonon. And then it becomes linearly dispersing at high q. And this mass kind of cuts it off. Okay, so that's the first step. The second step is to use ladder operators. So we write something like phi q is equal to square root. So now I'm going to use h bar equal to 1. Okay, because I'm lazy. And I write 1 over 2 omega q. And a dagger of q, a of q plus a dagger of minus q. Okay, and pi of q is equal to square root of omega q divided by 2, a of q, something like a of q minus a dagger of minus q divided by I.
What happened to the second term in the Hamiltonian?
Second term. Which term?
The C term, the C dependent.
It's in the omega q.
In omega q, okay. Right.
You mean this?
Yeah, I see.
C dependent. And then these under this transformation, right? We have that a of q, a dagger of q prime, for example, is 2 pi cubed delta 3 of q minus q prime. And the Hamiltonian then assumes the form integral d3q over 2 pi cubed. We have omega q, a dagger q, a q, plus 1/2 a q, a dagger q. Okay. Now this is a, maybe that's confusing like that. Now, okay, this, everything looks familiar, like harmonic oscillators. Basically, what did we do here? We first, we had a field. Okay, if I look at this Hamiltonian, what is it telling me? If I, for example, wouldn't have this C term, C equal to 0, then it would be like I have in each point in space, I just have a harmonic oscillator with frequency omega naught. Okay, it's basically like an infinitely dense set of Einstein phonons. This term, what it represents is basically that the field is basically some rigidity. It means that if I change phi in some location here, there is some stiffness. It doesn't want to develop derivatives. Too fast derivatives, they cost a lot of energy. And therefore, it's kind of like, imagine that you have, I don't know, like rubber or a bunch of masses on springs. If I move one of them, the other one also wants to move. Otherwise, there's a lot of potential energy stored in this thing. So this is what this term represents. Okay, now why am I saying that? I'm saying that because once we transform to momentum space, now it became exactly like this case where C is equal to 0. We have a bunch of disconnected or non-interacting harmonic oscillators. Just these harmonic oscillators, instead of being in real space, okay, they're infinitely dense, but they're in momentum space. So for each mode momentum, each one of them is not talking to the other one, and they're just like a harmonic oscillator. And the frequencies of these harmonic oscillators are given by this dispersion relation. That's basically what we did. And everything looks fine and good. But the only problem is that, you see this term? This term is like pi, right? It's like 4 pi cubed delta 3 of 0 and integrated over all space. So it's a lot of infinity right there. But what people typically say is that this is just a constant. Okay, so it's an infinite energy, very infinite, but it doesn't change the physics of the problem. So we just disregard it. Okay.
You can think like the theory must be a normal order, right? At the beginning.
Yes.
So from the beginning it was normal order, and this term doesn't exist.
Yeah. That's another way to avoid it. So what Joseph is talking about is that we can write our theories, instead of writing the theory just the way we did, you can write the theory minus, how does it go? You subtract the average, right? And that's equivalent to doing what is called as normal ordering. That means that the only terms that appear are where A dagger is to the left and A is to the right. And then you avoid these infinities. Yeah, okay. Now another comment is, because this is a course on quantum field theory, then I need to say that basically these, we understand now that these operators, A dagger and A, are creation and destruction operators of these kind of eigenmodes of the system, these waves. And this is what we call particles in quantum field theory. So for example, when you quantize the electromagnetic field, you also had these A and A dagger, and they were the creation and annihilation operators of photons. Okay? If I was describing optical phonons before, then this would be the creation and annihilation operators of phonons. Okay? And that's why we call them phonons. We call them phonons because we took a field, it was classical, we quantized it, and then we got this bunch of sharp excitations, and we call them phonons. An analogy to, say, photons. But these are not really point-like particles, right? They are actually extended waves, okay, with well-defined energy, living in all space. So you shouldn't think of them as like a small, like we want to think about a particle, like a point. Unless you want to think in momentum space in this case, then you can think of a point. But in real space, there's nothing close to a point. Okay. So now let's talk a little bit about Lorentz invariance, because one of the properties of this theory, where is it? This theory is that, at least when we wrote it in Lagrange formalism, it was obvious, is that it's Lorentz invariant. So remember that anytime you obtain a Lagrangian of a bosonic theory that has a second derivative in time and a second derivative in space, okay, then we usually associate it with some sort of Lorentz invariance. So to take advantage of this Lorentz invariance, we need to say a few words about Lorentz invariance. So the first thing I want to comment is, or let's put it this way, states that we might want to consider often is, one state is the vacuum state. This is the state that, if you act with A on it, it vanishes. And then we have P, is the state where we created one excitation with momentum P. And naively, we would want that to be A dagger P acting on 0. Right? And then that would imply that, say, Q and P is equal to 2 pi cubed delta 3 of P minus Q, which looks great, but the problem with it is it's not Lorentz invariant. It's not Lorentz invariant because a Lorentz boost, unlike a translation, for example, changes space. And if it changes space, there's going to be like warping of these momenta, and this warping will show up. So now, it's been a while since I did Lorentz transformations, so please correct me if I'm wrong. Let's assume we're doing a boost along the z direction. So then we have something like P3 prime is equal to gamma P3 plus beta, let's call it E. Okay, E. So P. What I mean is that P is a 4 momentum with E and P. Okay, and then E prime, the transform is gamma E plus beta P3. Okay, and gamma is 1 plus P squared over MC squared. Okay? And then that implies that D3 of P minus Q is equal to E prime over E delta 3 of P prime minus Q prime. So let's see if we can work that out.
Supposed to be minus in the gamma.
Minus. Okay, and beta, by the way, is, what is beta? Beta is this thing. P squared over MC, like this, right?
I think it's
The gamma is like 1 divided by the square root.
Gamma is 1 divided by the square root. Like that?
Right.
Okay, yeah, I told you it's been a while. Okay, So now, yeah, so how do we see this? We see this because we use, delta 3 of, say, p prime minus q prime is something like delta of p minus q divided by d p prime minus q prime, or maybe I'll write it. Let's do it easier. Delta of p is something like delta of p3 divided by d dp prime to dp, absolute value, and that turns out to be this gamma, I guess, right? Yeah. So instead, so to fix this, what we say is that the state P that we want to define is square root of 2 omega P, which is our A dagger P acting on the vacuum. And this turns out to be Lorentz invariant because, well, okay, let's see why. So P, first of all, P and Q now is going to be 2 omega P 2 pi cubed delta 3 of P minus Q. That's one thing. And if we define a unitary transformation that imposes the Lorentz boost on P, then we have this thing A dagger P U dagger of lambda is equal to the square root of omega lambda acting on P divided by omega of P A dagger of lambda P. Okay, where this lambda is the matrix that imposes the transformation. Yeah, and maybe I'll just give this as an exercise to show these different things. Yeah. And then to finish off today's lecture, let's talk about what we started from, which is the Lorentz invariance. So expectation values and correlation functions. Questions before I start? No questions, comments, complaints? Okay, so now with all this in hand, we can write the operator phi of x as some sort of sum over operators, right? So we can write this as an integral d3p over 2 pi q e to the I px phi p, which is equal to integral d3p over 2 pi cubed e to the I p x 1 over square root of 2 omega p times a of p plus a dagger of minus p, and therefore phi of x acting on the vacuum is equal to d3p 2 pi cubed e to the ipx divided by 2 times omega p ap plus a dagger of minus p acting on the vacuum. Now this guy destroys the vacuum, so we have a state here with minus p. So we can associate this whole thing as 1 over square root of 2 omega p. Because omega is even under p going to minus p, then this thing is just that. Okay? And then we have that phi acting on the vacuum is an integral d3p divided by 2 pi cubed e to the minus ipx. Here I took p to minus p, and then I get 2 times omega p times the state p that I've just defined before. And from here you can conclude that 0 phi of x times p is just e to the I p x. Okay. Now we can also do time evolution of these fields. So we write phi of x and t is equal to e to the I h t phi of x e to the minus I h t, and you'll find that it follows the same equations that you know and love. Namely, okay, so let's say we want to compute this thing. So the way to compute it is to use the eigen modes that diagonalize the system, e to the minus IHT. This guy is equal to minus omega pt a of p, and e to the IHT a dagger of p e to the minus IHT is equal to I omega pt a dagger of p. We'll do this in the exercise too. And therefore phi of x t is equal to the integral d3p over 2 pi cubed 1 over square root of 2 omega p ap e to the ipx minus I omega pt plus a dagger minus p e to the minus ipx plus I omega p t. Okay, sorry, this is plus. So I substituted the plus and minus here. Everything else transforms accordingly. So what people like to say is that this creates a particle propagating like a plane wave propagating, and this creates an antiparticle propagating in the opposite direction. Okay? Yeah. Also, we can.
How can you say it's an antiparticle? What is the charge?
Well, no, charge should be easy to see because this creates a particle, and this is destroys a particle.
Okay.
So, for example, if if you have we need to have a concrete example, but say we have some sort of concrete example where you create a particle at some point and then you destroy it at a different point. That would be like, creating the particle, letting it propagate, and then meeting an antiparticle and destroying it. It's a matter of interpretation. That's the charge is kind of the obvious part, I would say. But, okay. Yeah. So maybe. Okay, this is less important. Okay, so now let's compute a correlation function. So, using these results, what I wrote before in this, we can look at the vacuum expectation value of phi of x, phi of y. Okay, and this thing we will define as d of x minus y. Oh, sorry, that's not what I meant. Let's say these are 4 vectors. So what I mean by 4 vector, I mean that I evolve both in x and t, and say y and t prime. And this guy is equal to the integral d3p divided by 2 pi cubed 1 over 2 omega p. E to the minus I, and now I'm going to use the notation that this guy is like p mu x mu. Okay, so what I get in this case is p mu xu minus and this thing is evidently Lorentz invariant. Okay, and in fact, I don't know if I have this as a comment, but one can introduce, how does it go? Okay. I don't remember the details, but one can transform this integral into an integral over space-time, where this disappears and it just becomes this exponent. I don't remember the details, but maybe we'll also give that. Okay, but the point is that this thing is exactly the propagator that we had. This is basically k of say x mu and y mu, but instead of for the say Schrodinger equation that we had in the beginning of the class, this is for this Klein-Gordon theorem. Okay, but it's exactly the same thing. now, okay, so now the last comment I'd like to make is causality. So I see that we're going to finish a little bit early today, but that's fine. So we started today's class by claiming, sorry, this is actually, oh yeah, sorry. What I meant is this is the propagator. Feynman propagator for Kleinborg equation. Okay, so to conclude today's discussion, let's talk about this issue of causality. So, for example, we could take this expression and try to look at it and see if it respects causality. But because it's exactly the same propagator we had in the beginning of the class, you see that we have the same issue. So it means that the correlations can still be finite outside the light bulb. But as I don't remember who asked, Joseph, I think, the real thing we want to look at is not the correlations, but the expectation value of the commutation relation. Okay? So if instead we look at the expectation value of phi of x, phi of x mu, phi of y mu, then we find d of x mu minus y mu minus d of y mu minus x mu. And it turns out that this expression, and this I'll give it also in the exercise, this expression vanishes identically outside the light cone for space. So when this difference is space-like, this is identically zero, and when this expression is time-like, then it's non-zero. So that's how field theory basically solves this problem of causality. Okay? And yeah. So this is kind of a generic quantization for a Lorentz invariant scalar field. And I understand that you did see the quantization of the electromagnetic field, which is good. So in the exercise, I'll give exercises related to this and to the electromagnetic field, along the different things that we've discussed, and I'll send an email with an exercise. Okay? And if I don't, please remind me, because unfortunately these days I get very busy. I think it's important that you exercise this, because if we just talk here, hand wave and stuff, you won't really learn anything. Okay? Any other questions? Okay. And this is the book. Okay, that's perfect.
יונתן, יש מבחן?
כן, יש מבחן. נעשה, we'll do 50% of the grade is exercises and 50% is the exam. Okay, and the exam is not going to be too difficult. So
This is exactly the Baker Campbell also.
כן, כן, אפשר, אתה אפילו לא עברית, נכון? כן, אפשר להשתמש כמובן בזהות הזאת, אבל נגיד,
כי המתעניין שלנו מהפעם,
בוא אני אראה לך, בוא נזכר. לא, אז הדרך הנכונה לעשות את זה, זה באמת לקחת את המלפפון.